In this video, we will learn how to represent and draw linear programming problem in low dimensions. The first thing we need to understand is how to visualize an equation in two variables. So any equation of the form a1x1 plus a2x2 equal to b is a line in the plane, and such a line partitions the plane into two half spaces. So what is exactly this line? Well, this line consists of all the vectors x1, x2 that satisfy this equality. For example, let's have a look at the equation 3x1 plus 2x2 equal to 6. The points that satisfy this equation are those in this thick black line. For example, here you have the point 2, 0. So 3 times 2 plus 0 is exactly 6. And similarly here we have the point 0, 3. If you substitute once again, you obtain 0 plus 2 times 3, which is 6. The two half spaces are then 3x1 plus 2x2 greater than or equal to 6 on one side, and the same 3x1 plus 2x2 but now less than or equal to 6 on the other side. How can we easily check that? We can take a point in any of the two sides, for example the origin, plug it in, we obtain 0 plus 0 is less than or equal to 6, therefore all the points on this side are actually less than or equal to 6. Now we're interested in fixing A1 and A2, but changing B. What happens to our line if we do change this B? Whenever you change B, what happens is that you obtain a new line with the same slope but translated somewhere else. For example, in our example, if you change the right-hand side from 6 to 0, you will obtain a line parallel to ours but passing through the origin. An easy way to check that is to notice that the vector a1, a2 is always orthogonal to the obtained line. Therefore, all the lines with the same left-hand side will be parallel to each other. Let's now see an example. It has two variables, so we will be able to draw it in the plane. So here we're minimizing minus x1 minus x2 subject to x1 plus 2x2 less than or equal to 3, 2x1 plus x2 less than or equal to 3, and non-negativity on both variables. So the horizontal axis is always the x1 axis and the vertical the x2 axis. The non-negativity constraint x1 greater than or equal to 0 tells me that I must be on the right of this vertical line, because these are the values with x1 greater than or equal to 0, and vice versa, x2 greater than or equal to 0 tells me that my feasible region is above this horizontal line. Therefore, the two non-negativity constraints already tell me that my feasible region is contained in the non-negative orthant. Now we have to draw the remaining two inequalities, the yellow one and the blue one. So this is the blue one. How can I obtain it? An easy way, which always works as long as you have a right-hand side different from 0, is to just find the two intersections of the line with the axis. And this can be done by setting to 0 the first variable and then the second variable. So let's do it. If I set to 0 the x2 variable, I obtain 2x1 equal to 3, so x1 equal to 3 halves, and that's exactly the point here, and so I know that my blue line must pass through this point, 1.5, 0. Vice versa, if I set to 0 x1, I obtain x2 equal to 3, so I know that my blue line will pass through the point 0, 3. Now there's only one line that passes through these 2 points, and it's the one drawn here. So the points on these lines are exactly those that satisfy 2x1 plus x2 equal to 3. Now we need to understand what is the direction less than or equal to 3. In the picture, it's already visualized that it's the half space below the line. How can we check that? Well, again, let's take the origin. The origin is 0 plus 0 is less than or equal to 3, so it satisfies the inequality, and so the half space of the points that satisfy the inequality is the one containing the origin, therefore the one below the line. Now similarly, we can draw the yellow inequality. If we set x2 to 0, we obtain x1 equal to 3, so we obtain that the point 3, 0 is contained in the yellow line. Vice versa, if we set x1 to 0, we obtain x2 equal to 3 halves, and so we obtain that the vector 0, 3 halves passes through our line. So we can draw these 2 points. Here they are, 3, 0 and 0, 3 halves. And we can draw the yellow line passing through them. Again, we have to understand what is the half space of the vectors that satisfy the inequality. We plug in the origin, and the origin does satisfy it, so it's once again the half space below. So now we have identified the feasible region. It is the set of points that satisfy all our 4 inequalities, and it is highlighted by the vertical lines. Finally, we also want to visualize the objective function. In order to do this, we visualize the family of lines minus x1 minus x2 equal to sum b. We know that we obtain a family of parallel lines. For example, with the right-hand side of minus 2, you will obtain this line, and with the right-hand side 0, you will obtain the parallel line passing through the origin. One important thing to notice is that the vector of the left-hand side, which is minus 1, is visualized over here, always points in the direction where the right-hand side increases. Now we have all the ingredients that we needed to identify the optimal solution to this very simple problem. So why is that? In fact, in this optimization problem, our task is to minimize the objective function. So we want to essentially shift our red inequality as much as possible in the direction opposite to the red arrow, because in the direction of the arrow you increase the right hand side, and we want to decrease it as much as possible because we're minimizing. So geometrically what we're doing is we're shifting this red line as much as possible in the direction opposite to the arrow, so in this case essentially up, and we should stop exactly when we are about to leave the feasible region. So when the intersection between the red line and the feasible region is about to become the empty set, which means that we're going to stop in this point here. So why are we stopping here exactly? Well, this is because this is a feasible point, of course, it's in our feasible region, that is on this red line, so its objective value is minus 2, and if we move this red line just a little bit more up, then we obtain a better objective value, but there will be no feasible point at all on the line, and so we're not able to find a better solution than our vector here, 1, 1. We have now understood how we can visualize a linear programming problem in 2 variables. The technique that we used actually can also be used in 3 dimensions. There are only few differences, in fact. The first one is that the set of points that satisfy an equation will be a plane instead of a line. Similarly to the 2-dimensional case, the plane will be perpendicular to the vector c, and so the objective will be to slide this plane as much as possible in the direction of minus c, so again in the opposite direction with respect to the arrow represented by the vector c. And we're going to do this as long as we don't leave the feasible set. So we're going to stop just before leaving the feasible set. Here is a picture that is supposed to be 3-dimensional. The feasible region is super simple. It's xj between 0 and 1 for every j. So we obtain exactly the 0, 1 cube. And the objective is to minimize minus x1, minus x2, minus x3. So we can either draw C and move the corresponding plane in the opposite direction, or maybe we can simply just draw immediately minus C, which is 1, 1, 1, and move our plane in the direction of minus C. If you visualize the plane given by minus x1, minus x2, minus x3 equal to some right-hand side number b, you will then understand that in this linear programming problem, the optimal solution is given by the vector 1, 1, 1. Please try to do that, and notice that this graphical approach is only useful to give us an idea of how this problem looks like and what an optimal solution could be, but especially in 3 dimensions, when you start to have many inequalities and not as simple as this one, then it can become, of course, tricky to even visualize or draw such a problem. Both the examples that we have just seen have a similar structure in the sense that in both of them we have a feasible region that is bounded and the problem has just one optimal solution. But this doesn't always happen, and to convince you, I will now show you a bunch of examples where different things happen. I'm going to use the same feasible region with a bunch of different objective functions at first. Our feasible region is this gray area over here that extends to infinity here on the right. This is the feasible region given by these three linear inequalities. We have non-negativity, which immediately restricts us to the non-negative orthant, and then we have the inequality minus x1 plus x2 less than or equal to 1, which gives us the half space below this line. As I said, we're going to consider different cost vectors C, and they're all visualized in this picture. So we're going to start with this one, C equal to 1, 1. In fact, we're minimizing x1 plus x2. In this case, we're moving the line orthogonal to the vector C, which is this one over here, downwards as much as possible, and so our optimal solution will be the origin. Also in this case, the optimal solution is unique. However, what happens if we instead look at the objective function x1? So x1 gives us the vector 1, 0, which is visualized here. The lines orthogonal to C are exactly the vertical lines, and we're moving left as much as possible. So the origin is still an optimal solution, but so is the vector 0, 1, and actually so is every point in the segment joining the two solutions we just talked about. So in this case, we have multiple optimal solutions. We have an infinite number of optimal solutions indeed, but the set of optimal solutions is bounded because it's this segment here, and so it doesn't extend to infinity in any direction. Let's now try a different objective function. Now we minimize x2, so the vector C is now 0, 1, and it's visualized over here. Now our lines orthogonal to the vector C are horizontal, and we want to go down as much as possible. So once again, the origin is an optimal solution, and so is any point along this half line. So in this case, I again have multiple optimal solutions, still infinitely many, and the set of optimal solution is unbounded because it extends to infinity on the right. In our next example, we're now minimizing minus x1 minus x2, so our vector C is minus 1 minus 1, and it's represented here. So now the orthogonal lines are something like this, and we're moving upwards as much as possible, and you can see that we can move our line upwards as much as possible, and we will always intersect the feasible region, since the feasible region goes to infinity on the right. Therefore, in this case, we can obtain feasible solutions which are better and better, and their cost converges to minus infinity. In this very special case, we say that the optimal cost is infinity and that the problem is unbounded. Let's see now one more example. And for the first time, I want to change the feasible region that we were looking at. I only want to introduce one more inequality, which is this one, x1 plus x2 less than or equal to minus 2. So below here you can see all the inequalities describing the feasible region. It's exactly the same as before with my three old inequalities plus this new one. So on the right here I still have the picture of my old feasible region, and the new inequality, if you think about it for a minute, will give me a line somewhere like here, and the set of points that satisfy the inequality will be the set of points that is below this line. Therefore, no feasible solution exists to my new linear programming problem. In the previous example, we have seen that the outcome of a linear programming problem can have many different possibilities. And we have seen exactly four possibilities. The first possibility is where there exists a unique optimal solution. Another case is where there exist multiple optimal solutions. And we have seen two different types of example. In one, the set of optimal solution was bounded, and in another one, it was unbounded. Then we have seen an example where the optimal cost is minus infinity, and so no feasible solution is optimal. Finally, in the very last example, we have seen that the feasible set can be empty. We will see later in the course that these are essentially all the different possibilities that can happen in linear programming. Another key observation is that in all the examples that we have seen that have optimal solutions, there always exists at least one optimal solution that can be found among the corners of the feasible set. And for now, I'm not going to define formally what these corners are, but it's clear that I'm referring to the vectors 0, 1 and 0, 0. In the next chapter, we will also show that this always happens in linear programming problems, as long as the feasible set has at least one corner. So far in this video, we have learned how to visualize general form problems in dimension 2 and 3. Next, I want to tell you a little bit how you can visualize problems that are in standard form. Here is a linear programming problem in standard form. So how can we visualize it? Well, the answer is fairly obvious. In fact, we can visualize it exactly as we have done so far. If the dimension of x is at most 3, then we know how to do it. For example, if my feasible region is x non-negative and x1 plus x2 plus x3 equal to 1, then we can draw it in dimension 3 and obtain this triangle here with corners 1, 0, 0, 0, 1, 0, and 0, 0, 1. Unfortunately, while for general form problems in dimension 2 or 3 we can obtain fairly interesting problems already, in dimension at most 3, standard form problems can't look that complicated because of the special structure of a standard form problem. In fact, if you think about it, if you have a bounded feasible region, you can quickly realize that you will have either a triangle or a segment or a point. Fortunately, in the case of standard form problems, we are sometimes able to visualize the problem even if the dimension of n is greater than 3. So let's have a look at the standard form problem. And as we always do, we assume that the matrix A is m times n. This means that the vector x has dimension n, and we have m equality constraints. Let's assume that m is less than or equal to n, and that A has full rank. This constitutes the most interesting case, and it implies that our vector x must lie in the n minus m dimensional set of the vectors x that satisfy the system of equalities Ax equal to b. In our previous example of the triangle in R3, we had n equal to 3 and m equal to 1. So we obtained a two-dimensional set in that case. And the two-dimensional set is the unique plane that contains the triangle. The idea then is that we don't need to visualize anything that doesn't lie in that n minus m dimensional space. And in our n minus m dimensional set, we are only constrained by the remaining constraints defining the feasible region, which are only the non-negative inequalities. The number of these non-negative inequalities is exactly n. So, for example, if n minus m equal to 2, then we can draw our feasible set as a two-dimensional set defined by n linear inequality constraints. Let's get back to the only example we have seen so far of a standard form problem. We draw the feasible region directly in the original dimension 3 as this triangle. But now, thanks to our observation, we can draw it in the plane, and essentially our plane will be the unique hyperplane that contains this triangle. So if we then live in such a plane, we only have to draw the three inequalities xi greater than or equal to 0, which then will give us a triangle. Now, this is very intuitive from a geometrical perspective. However, from an algebraic perspective, it's really confusing if you think about it for a minute. Because how can you draw x1 greater than or equal to 0, x2 greater than or equal to 0, and x3 greater than or equal to 0 in the plane, which is a two-dimensional space, and of course you don't have three variables? Well, algebraically, the idea is to use the equations to reduce the number of variables. So once again, let's look at our standard form problem x1 plus x2 plus x3 equal to 1. We use the equality to eliminate one of these variables. We can choose, for example, to eliminate x3. So we can write x3 in terms of the remaining variables. And so x3 is equal to 1 minus x1 minus x2. Then we substitute in the inequality constraints that we have to draw. x1 and x2 greater than or equal to 0 don't change because there's no x3 involved. And x3 greater than or equal to 0 becomes 1 minus x1 minus x2 greater than or equal to 0. In other words, the feasible region is then described by x1, x2 greater than or equal to 0 and x1 plus x2 less than or equal to 1. And if you draw this, in fact, you obtain a triangle, as you should. Now I'm sure that you have a question. Namely, why did we choose to eliminate x3? I mean, eliminating x3, it's clear we obtain this system over here, but what if instead we substituted x2 or x1? In this example, due to the symmetry of our equation, you would have obtained something very similar. For example, if you eliminated x2, you would have obtained x1 plus x3 less than or equal to 1, x1, x3 greater than or equal to 0. However, in general, you will obtain very different systems depending on which variable you decide to eliminate. This might seem strange at first sight, but really it's not. The fact is that all these different systems that you would obtain by choosing to eliminate different variables are all equivalent because of the equality constraints that allowed us to eliminate these variables in the first place. Finally, I want to make one last important comment regarding visualizing standard form problems. In the running example that we analyzed, we had a standard form problem which lives originally in R3, and then we introduced a technique that allowed us to visualize it in R2. Now, this is just an example. In fact, it's not so useful because we could already visualize this problem in R3, which is great. However, this technique allows us to visualize very high dimensional problem. In fact, as long as n minus m is equal to 2, then no matter how large n is, we can visualize such standard form problem in dimension 2. And we're going to use this technique several times throughout the course. Similarly, even if n minus m is equal to 3, then instead you can visualize any high dimensional problem in dimension 3. So if we keep n minus m, for example, equal to 2 and increase n, we can always visualize these problems. What will change is only the number of inequalities, because the number of inequalities is always n, because you have n non-negativity constraints. Throughout this course, we will see many linear programming problems, and we're always going to discuss both the geometry of the problem and the algebra of the problem. And I strongly encourage you to understand how to visualize linear programming problems following the techniques that we have discussed in this video, because this is crucial to get an intuition behind this type of problems. And this concludes this video and also the first chapter of our course.